Welcome to today's session on the predictability of stock returns using tri-signal predictive equity analytics with dynamic state space. We introduced tri-signal, our new predictive equity analytics with dynamic state space framework, and walk through equity return time series behavior prediction including change points. This cutting-edge tool is designed to help investors navigate the unpredictable nature of the financial markets by providing insights to avoid market downturns as well as capture upturns. Tri-signal predictive equity analytics with dynamic state space leverages advanced algorithms, machine learning, and big data analysis to provide accurate predictions. Key features include 1. Dynamic state space framework. Our framework adapts to changes in the market environment and aligns with the evolving dynamics of equity markets. 2. Risk mitigation strategies. Our tool provides insights that identify downturns, manage risk exposure, and implement effective risk mitigation strategies. 3. Opportunity identification. By analyzing a wide range of market indicators and patterns, our analytics help investors uncover upturns and identify investment opportunities that would be overlooked. If algorithmic trading is dominating the US markets, can we detect it? If we can detect it, how can we use it to our advantage to predict future returns? Let me define predictive equity analytics. Tri-signal predictive equity analytics with dynamic state space is an analytic framework that predicts the price movement of individual stocks or portfolios with accuracy surpassing 90% over future 1 to 5 trade days. It is based on extracting a set of price signals, signal 1, signal 2, and signal 3, that facilitate dynamic state space representation of price movements. Predictive equity analytics with dynamic state space framework integrates many distinct fields of study. Each night, roughly 15,000 US equity symbols are processed. ETFs, mutual funds, and stocks, approximately 12,000 symbols are output and available prior to market open. The approximate 12,000 symbols output have structure and a degree of predictability that varies by equity symbol. The approximate 3,000 symbol difference input versus output are equity symbols that have no structure and are truly random. We focus our analysis on the equity symbols that have structure and a degree of predictability. Here is a sample report for Invesco QQQ Trust 1 with ending trade date May 30. We want to create predictive reports that are easy to interpret. Here the yellow rows are biweekly pay dates. If a person had this report available prior to market open, you see that a mechanical buy and hold strategy is suboptimal. We analyze Invesco QQQ frequency and average trend using 60 trade day matrices, rolling every 20 trade days. For frequency and average trend, observed signal plus noise matrix ABC on the left with yellow highlight is partitioned into core signal C matrix in middle with light orange highlight. Noise matrix AB on the right is highlighted in light green. Noise matrix AB is composed of outliers matrix A and heavy variance matrix B. Here, we look for changes in core matrix C over the time steps t equals 0, t equal -20, t equal -40, and t equal -60. We find heavier variance contribution in the most recent matrices. Now, think back to your linear algebra class. Can we get more information if we calculate determinants, eigenvalues and eigenvectors? You bet. Some folks like graphs and others like matrices. True analytics folks will want it all, including eigenvalues and eigenvectors. Tri-signal predictive equity analytics with dynamic state space is the breakthrough folks have been working on for the last 50 to 60 years. The strategic goal is optimal wealth management. Wealth management in this context means faster rate of wealth accumulation and downside protection. The optimal wealth management effect is portrayed in the above graph comparing a risk-free account with a tri-signal predictive equity analytics with dynamic state space account. Protects against downside, you say? Detects change point and captures upside, you say? You are thinking, seems too good to be true. How is this possible? Predictive equity analytics with dynamic state space can estimate current eigenvalues and eigenvectors for a discrete approximation to continuous time varying Fokker-Planck probability distribution. Transformation in 2 modes, 1, signal plus noise, and 2, core-only signal. At points in time where dominant eigenvalue changes in excess of a threshold, a change point has occurred. Upon change point detection, analysis of future behavior of up, horizontal, down can be determined. Also note, predictive equity analytics with dynamic state space can also filter out Poisson outliers to a separate matrix. To my left is a 3D depiction of continuous time varying Fokker-Planck equation and trisignal predictive equity analytics with dynamic state space 3 by 3 by 3 cube matrix. Up until this presentation, only the state direction transformation could be estimated with any degree of accuracy. For small enough time steps, one could assume no change in shape and waving hands that we are at full stationarity with a closed-form solution. Predictive equity analytics with dynamic state space key result is as follows. The ability to estimate the change in distribution in time direction as well as estimate change in state direction. At t equals 0, using vector cross product we can estimate the average height of the density curve which as goes higher, the tails must shrink and vice versa. Predictive equity analytics with dynamic state space is based on a time-varying form of a Merton-like return equation. At the end of each trade day we observe the close price and estimate the drift term mu, volatility, and outlier point mass indicator. Volatility is measured by signal 1 in the framework. Signal 1 strength less than 1 correlates to heavy variance matrix B. Signal 1 equal to 1 correlates to pure point mass outlier matrix A. In the framework, we designate signal 3 as drift. You can see that predictive equity analytics with dynamic state space momentum is defined as the change in the rate of drift, mu. This differs from standard momentum definitions. We will see in coming slides that a 3 by 3 matrix representing 9 state spaces will form our eigenvalue, eigenvector analytic foundation. Predictive equity analytics with dynamic state space generates predictive reports prior to market open each trade day. In calculus, the behavior of a function can be analyzed by studying its derivatives. Here is how the correspondence between predictive equity analytics with dynamic state space signals and function analysis can be understood. 1. Signal 1 indicates a local optimum or an inflection point. Point 2. Signal 3 indicates the behavior of the function as down, horizontal, or up. Down refers to a decreasing behavior of the function in a specific interval. Horizontal indicates that the function remains constant or has little to no change in that interval. Up signifies an increasing behavior of the function in a specific interval. Signal 3 can represent any of these behaviors, helping us to analyze the increasing or decreasing trends of the close price-based equity return process. By observing these signals, we can gain insights into future trade days' equity return time series local optima, inflection points, and overall behavior in different future intervals. Notice that for Invesco QQQ, as signal 3 level dropped, so did the macro behavior of the price return series. In addition to signal 3 level, we also see signal 3 negative momentum as also being predictive. You can also see that signal 1 equal to 1 correlates to local optimas and inflection points. The January 23rd, signal 1 equal to 0.7 combined with signal 3 less than 0.95 indicated a sell action. We form a 3 by 3 state space representation using for column signal levels, low, medium, high. Rows represent momentum of drift term. Row 0 is positive momentum. Row 1 is no momentum and corresponds to standard model, and row 2 is negative momentum. Analysis bases include frequency or counts, average trend, and combined frequency percentage multiplied by average trend. Additionally, we proceed to further partition combined signal plus noise matrix ABC into core signal matrix C and combined heavy variance matrix B and outlier matrix A. We refer to this process as signal detection in a noisy background. Matrices are formed at points in time, t-60, t-40, t-20 and t-0. For each time point the dominant eigenvalue and eigenvector are determined and changes therein for metastate direction are noted. In coming slides, we will rearrange these matrices by signal level and momentum and perform similar analysis in time direction. The importance of core signal quantification compared to that of observed combined signal plus noise is demonstrated. In this case, the core signal has significantly decreased while volatility has increased. Without the use of predictive equity analytics with dynamic state space, this change would have gone unnoticed, the result of which is a significant increase in volatility or risk. We are interested in learning the extent to which noise matrix AB impacts our analysis. Thanks to predictive equity analytics partition of the time series into components, we can proceed with direct calculations. We calculate eigenvalues for matrix ABC and separately for matrix C. We compare the maximum absolute eigenvalue for matrix ABC to that of matrix C. The difference tells us the degree to which noise impacts our analysis. We are keenly interested in core signal matrix C eigenvalues and eigenvectors as they represent the local time long-run behavior of the equity close price time series. We perform similar analysis for time points t-60, t-40, t-20 and t-10. We perform similar analysis from last slide for the following time points t-60, t-40, t-20 and t-10. From this information, we know the meta-state effect holding time constant at t equals 0. We want to calculate the effect due to time change, holding meta-state constant. We can do this by rearranging our of matrices into signal level and momentum for 3 contiguous time points. We have low signal with 3 columns of momentum, medium signal with 3 columns of momentum and high signal with 3 columns of momentum. Given our data, we therefore have 2 sets of matrices and can measure change from t-20 to t-0 in time direction by signal level. It should be no surprise that we perform dominant eigenvalue and eigenvector analysis. We have come full circle to our initial preview slide. Predictive equity analytics with dynamic state space framework reliance on 3x3x3 cube enables dominant eigenvalue analysis, which is the spectral solution to the discrete Fokker-Planck approximation equation. We now illustrate change point detection using dominant eigenvalue and eigenvector analysis in the following slides. All matrices use 60 trade days with a rolling 20 trade days window. The combined noise matrix ABC is partitioned into core signal matrix C and combined heavy variance matrix B plus outlier matrix A. We perform dominant eigenvalue and eigenvector analysis. We concentrate on detecting a change point using core matrix C and for combined signal plus noise matrix ABC. We find medium signal is dominant, but the eigenvalues in metastate direction are decreasing as we move from t-40 to t-20. How is change point detection affected by using signal plus noise matrix ABC as compared to core signal matrix C? On a signal plus noise matrix ABC basis, the difference of dominant eigenvalues is 0.04. Using core signal matrix C, medium signal is dominant, but the dominance is slightly less at 0.03. The fact that analysis based on signal plus noise versus signal only yields similar results bolsters credibility. We rolled 20 trade days forward, which brings us to time t equals 0 and perform eigenvalue analysis on each of low signal, medium signal and high signal. We find medium signal is dominant, but the eigenvalues in metastate direction are decreasing as we move from t-40 to t-20 from 0.48 down to 0.44. Using signal plus noise matrix ABC as our basis, we find the following. Eigenvalue analysis for high signal detects a change point. High signal eigenvalue is 0.48, which is greater than medium signal eigenvalue of 0.44. To predict down, horizontal, up behavior, the average trend and frequency matrices are analyzed as second step. The infographic on my right visualizes change point. The classic sign is 180-degree rotation in 3-dimensional space. Here we started with red vector pointing below the plane at previous measurement, and with current measurement the vector has rotated in points in direction above the plane. Predictive Equity Analytics Signal 3, which was the drift term, is the leading predictive variable since the level and momentum have primary effect as depicted in the 2-dimensional contour map. Signal 1 represents volatility and is a lagging predictive variable as depicted in the dispersion of the 3-dimension Fokker-Planck probability distribution transformation. How can we detect the first eigenvalue change? Simple. We perform the same analysis using different rolling trade days windows. For example, we use rolling trade days ranging from 20 to 10 to 5 and to 1. Change point is characterized as either a switch in signal or same signal with dominant eigenvalue change exceeding some threshold. Predictive equity analytics with dynamic state space has been operationalized. Since mid-2018, we scan over 10,000 U.S. equity symbols each trade day prior to market open. Instruments include REITs, ADRs, ETFs, mutual funds and stocks. Predictive Equity Analytics with Dynamic State Space user interface is Microsoft Excel based. Look for a free demonstration version with datasets updated each trade day prior to market open coming soon to the Microsoft Store. Predictive Equity Analytics with Dynamic State Space Framework enables the user to avoid market downturns as well as capture upturns through change point detection and estimation of eigenvalue. Eigenvector to determine behavior with accuracy exceeding 95%. Predictive reports that are easy to use and interpret include 1. Graphs, 2. Matrices, and 3. Dominant eigenvalue, eigenvector. Predictive Equity Analytics with Dynamic State Space has been operationalized. 5+ years of observation in U.S. markets. Over 10,000 equity symbols. Accuracy exceeds 95%. 100% accurate avoiding market downturns. Please see the appendix for references in support of Predictive Equity Analytics with Dynamic State Space. Thank you for your interest in Predictive Equity Analytics with Dynamic State Space. If you have any questions regarding this topic, feel free to ask, and I'll do my best to answer you. As you may have guessed, our next project is to provide on-demand customized investment analytics using Predictive Equity Analytics with Dynamic State Space and Deep Brain. The future is bright. I'm going to need virtual shades.